Okay, so I gave this talk at Notre Dame 2 days ago. And initially, well, I had wanted them to record it, but I sort of forgot to ask them. And I think they also had some intention of recording these things, but like they forgot to ask me or set it up or something. So I thought I'd do it over again and record it. Partly because, we put out a paper recently on this topic, and I think that paper, it's pretty heavy on the algebraic geometry side. And it's probably a bit much for model theorists, for a lot of model theorists. But I do think that the stuff in this paper, hopefully is still pretty interesting to model theorists. So I think it's worthwhile to have an exposition that's really designed for, people who have only the fuzziest understanding of model theory. And that's what this is. So this is essentially going to be the talk I gave in the Notre Dame seminar. But without on-end asking questions. So all of this is joint with Will Johnson, with Min Tran, and Vincent Yi. So as the title indicates, I'm going to be talking about a topology, and this topology is defined in an arbitrary field. So that's literally true, but it's morally false, because this topology is often discrete. Over many particular fields, you just get a discrete topology, so it doesn't really count. But it turns out that the fields where this topology is non-discrete, that this is some known and interesting class of fields. This is what are called large fields. So before I talk about the topology, I'm going to spend a slide or two just discussing large fields and largeness, because I don't know how well known this is, among model theorists, although I do think it is. This should be a very interesting notion to model theorists for reasons that I'll explain. So yeah, K is always a field. So here's my first definition of largeness, which is that your field is large if whenever we have an irreducible K-curve, irreducible curve over the field, and if it has a smooth K-point, then it has infinitely many K-points, right? This is the standard notation for the set of K-points on the curve. So I understand that, right, this definition involves, some algebraic geometry to understand. So on the next slide, I'll give a sort of more down-to-earth version of this definition. Before I do that, I give this second definition that's maybe more accessible for model theorists, right, where largeness is equivalent to saying that the field is existentially closed in the field of Laurent series with coefficients from K. So that's equivalent to being large. Now, I'm not going to use this definition in this talk at all, but it's maybe worth pointing out that this really is actually used quite a bit in the literature, including, in the literature of people who are really field theorists. Right? If you think about it, what this really says, right, is that if you have a system of polynomial equations and inequations with coefficients from K, and if it has a solution in this field of Laurent series, then it has a solution in K, right? So that's really, right, you don't need to be a model theorist to understand that property. So just as a historical note, this notion isn't too old. It was introduced in the mid-90s by Pop. So Pop was interested in some Galois theoretic statement that I'm not going to try to explain because, it's a bit technical. But this is just a statement that had been proven for various specific fields or specific kinds of fields. And Pop realized that largeness was the property that you really needed to prove this result, right? That was what these fields, the property that these fields had in common that made this work. And so in particular, he used this to solve the inverse Galois problem over the field of rational numbers, the field of rational functions with coefficients from K. So that, and since then, large fields have been extensively studied in Galois theory. You can do a lot of Galois theory over large fields, but also more and more they've been studied in in other areas, like like in algebraic geometry or field theory, and also maybe now more into logic too. So it's not like a definition that's like initially obvious, or initially natural, but somehow this is a class of fields over which we can do a lot of interesting mathematics. Okay, so I'll give some examples of large fields in the next slide, but first I want to give some examples of fields that are not large. Okay, so here let's consider. I'm going to show that the field of rational numbers is not large. Okay, so let's let C be the curve given by x to the 4 plus y to the 4 equals 1. Okay, so this is a smooth curve. So here I have a picture of the real points of this curve, which, as you can tell, is nice and smooth, no singularities. Okay, but it's a pretty, I think, reasonably famous theorem of Fermat that this curve has only 4 real rational points. Right? Okay, so rational number is not large. That exactly witnesses it. Okay, now number fields are also not large. Okay, now I say that here, I say that's because of the Mordell conjecture, right, which is a theorem. Okay, now I'm sure this is tremendous overkill. I'm sure there's some much more elementary way to show this, right? But I say it's due to the Mordell conjecture because that gives a nice high-level explanation of why it's true, right? So the Mordell conjecture, okay, I'm not going to say what this is precisely, but what it says is that if you have a typical curve over a number field, then it has only finitely many points from that number field, right? Like a sort of a generic curve of only finitely many points, and so okay, if you have something like this, it's easy to cook up counterexamples to largeness. Okay, and there are other fields, other than number fields, over which, some kind of Mordell conjecture holds. So like if you take, function fields, say in particular the field of rational functions over any fields, again, there's some kind of Mordell conjecture. Okay, now it's more complicated than the Mordell conjecture over number fields, but it still says that, like typical curves have only finitely many points. Okay, so, I think of large as meaning like anti-Mordelic, right? Where anti-Mordelic means, so by anti-Mordelic, I don't mean that Mordell conjecture fails, but like the opposite of the Mordell conjecture. Okay, so I think it's worth pointing out that, if you sort of look at the examples of particular fields of interest, okay, at least from what I've seen, it seems like, they're typically either large or satisfy some form of the Mordell conjecture. Okay, now I don't mean to suggest there that there's some kind of general dichotomy. I'm sure there isn't. But at least there's a bit of an empirical dichotomy among fields of special interest. Yeah, and it's also worth pointing out, right, that these, these kinds of fields are like exactly the fields that model theorists like don't really work with, right? Like number fields are, for example, are completely wild, right? They're all bi-interpretable. Okay, I think, at least mutually interpretable. Maybe I should be careful there with the integers. Okay. And so as far as I know, every example of a model theoretically tame field is large. And again, I don't mean to suggest that there's some general theorem that's true there, but at least, this covers the examples. Okay, so now let me talk about some examples of large fields. Okay, and my first example is just going to be the field of real numbers, right? Which of course is one of the, main examples of a model theoretically tame field. Okay, so I state, to see this, I state this more down-to-earth definition of largeness that I promised, okay? So suppose that we have an irreducible polynomial in 2 variables. Suppose that it has a solution in the field, and suppose that the second partial derivative is non-zero at that solution. Okay, then largeness is equivalent to saying that whenever this happens, the polynomial has infinitely many solutions. Okay, so why is this equivalent to the first definition? Okay, so first of all, the first definition is some statement about, just irreducible curves. Okay, but you can reduce this to the same statement for irreducible plane curves. Okay, and that's basically because any curve is birationally equivalent to a plane curve. Okay, now what does this derivative condition here mean? Okay, that means 1, that the point is non-singular, and 2, that the tangent line at the point is not vertical. Okay, and if you have a curve with a non-singular k-point, you can always apply some affine transformation to make the tangent line at that point not vertical. Okay. So, up to like sort of a change of coordinates, this is just saying that the curve is non-singular. Okay. Yeah, so hopefully this is more, comprehensible. Okay, so now why are the real numbers large? Okay, well this definition is set up to just allow us to like directly apply the implicit function theorem, right? So the implicit function theorem implies, okay, roughly speaking, it implies that locally, the curve looks something like this. Okay, more precisely, for any real number a prime close enough to a, there's a b prime, so that a prime b prime are a solution of the polynomial. Okay, so what do we need here? What we need is some form of the implicit function theorem, at least for polynomials. Okay, and then there's a lot of other fields that satisfy an implicit function theorem for polynomials. Right, so like, this works just as well for any real closed field. Okay, now it also works for Henselian valued fields. Okay, so I don't want to, define the notion of a Henselian valuation, so if you don't know what this means, just think about these examples, right? So like the p-adic numbers, or any algebraic extension of the p-adic numbers, or fields of formal power series are Henselian, right? It's like the field of Laurent or the field of Puiseux series with coefficients from an arbitrary field. Okay, and these kinds of examples cover like, I don't know, they already cover a lot of the Henselian valued fields that at least I actually care about. Okay, now I also say more generally, so the point is for Henselian valued fields, you have the implicit function theorem for polynomials. Okay, and I say this more generally for T Henselian fields. So let me just say a word about what this means, because we'll see it again. So the T here stands for like topological, right? So Henselianity is a property of valuations on fields, and T Henselianity is a property of field topologies. It's like the analogy. And in fact, one way of defining this is to say that, a field topology is T Henselian. Okay, the definition involves, like maybe two things, and one of them is some kind of implicit function theorem for polynomials. I'll just say the reason I like this and that it's not useful to work with is that this is a notion of Henselianity that includes real closed fields. So the order topology on any real closed field is T Henselian. So in particular, the real numbers are T Henselian. Okay, and then a T Henselian field is just a field that has a T Henselian field topology. Okay, so all of these examples are fields that are large for some topological reason. Like the proof of largeness involves something that's stated in terms of a topology. Okay, but there are also examples of large fields that are large, for some non-topological reason. Right, so like one example is pseudo-finite fields. Right, that means, infinite models of the theory of finite fields. You can think of these as, ultra products of finite fields, or infinite algebraic extensions of finite fields. Okay, now these guys, there's some overlap between these two. So like infinite algebraic extensions of finite fields are often pseudo-finite. Okay, but also they often aren't. Okay, so how do you prove that these kinds of fields are large? Okay, it's a consequence of the Hausy-Weil estimates, right? These are estimates for the number of points on a curve over a finite field. It's a special case of the long-Weil estimates. Okay, so here, largeness falls for sort of a number-theoretic reason. Now, in either case, the Hausy-Weil estimates actually give you something stronger. It gives you a property that's called being pseudo-algebraically closed, or POC. Okay, which I won't define, but okay, it's worth mentioning this because there are other examples of POC fields, and there's also a general study of POC fields. There's a line of research, both by model theorists and field theorists on POC fields. Okay, now there's quite a few other examples. And one example I should have put on this slide is just algebraically closed fields, or more generally separably closed fields, okay, which are just large because, basically every equation has a solution. But I also mentioned pseudo-real closed fields. And I mentioned that because this is an example that there's been some model theoretic work on these recently, right? So these include, for example, the maximal totally real extension of the rationals. Okay, but also like pseudo-p-adically closed fields and other things like that. Okay, so now I've talked about largeness, right? Okay, and so we saw that for quite a few fields are large for some topological reason. So what we're going to see now is that if you have a large field, you can always construct a reasonable topology on it. Okay, now so that's what I'm going to do on the next slide, is I'm going to start describing this topology. Okay, now this topology, as the title of this talk indicated, is defined in terms of etale morphisms. So I need to say something about that. Okay, now I don't want to give the actual definition of an etale morphism, because it's one of these definitions that's not useful unless you already understand it in some sense, right? Like if you don't know it, you're not going to learn it from a slide. Okay, but it's worth pointing out that in the nice case where we have smooth varieties over a field, the definition of etale becomes simpler, right? An etale morphism in this case is just a morphism that induces isomorphisms between tangent spaces, right? So, if you're talking about smooth manifolds and C infinity functions, right, if we're in the setting of differential geometry, this is exactly the condition that ensures that the function is a local diffeomorphism. Okay, so etale morphisms are like the algebraic analog of say, local homeomorphisms. Okay, so now I need to define this notion of an etale image. Okay, so if we have an etale morphism between two varieties, right, and here V and W, they aren't necessarily smooth. Now these are arbitrary varieties over K. That induces a map from the K points of the first variety to the K points of the second, and the image of that map is what we call an etale image. Okay, so first of all, first fact about etale images is that they're closed under finite unions, closed under finite intersections, and contain all Zariski open sets. So that this is enough to say that the etale images form a basis for a topology on the K points of W that we call the etale open topology, and that in these slides I'll use this symbol for just to save space. So yeah, open sets in this topology are unions of etale images. Okay, so this line here, I'm not going to say anything about the proof, except that it's an easy consequence of standard facts on etale morphisms. It's just a matter of citing the right things from EGA. Okay, so now we have a topology on the K points of an arbitrary variety over K, right? But we also want to know that these topologies interact nicely together. So that's what these next facts say, right? So for example, if we have any morphism between K varieties, the induced map from the K points of one to the other is continuous when both the domain and range are given the etale open topologies. So for example, in particular, this says that if we have like a single variable polynomial, that gives us a continuous map from the field to itself, which is useful. If the morphism is etale, the map is actually open. Okay, now the fourth definition, what this is about the situation where one variety is a subvariety of the other. Okay, so now in this setting, there are two like natural topologies to put on the K points of the subvariety, right? First of all, we could, think of the subvariety just as intrinsically as a variety that's on its own and put its etale open topology on the K points. Okay, the other thing we could do is we could take the etale open topology on the bigger variety and restrict it down to the K points of the subvariety. Okay, what this says is just that these two topologies are always going to agree. Okay, and that's often very useful. Okay, and so, again, I'm not going to say anything about how to prove these items except that they're all easy consequences of standard facts about etale morphisms. Right, so, of course it takes, a good amount of work to build up this whole theory of etale morphisms, but once you have it, you just need to cite the right things from EGA and then interpret them into this language. Okay, now the etale open topology on the field may not be a field topology. Sometimes it is, sometimes it isn't. We'll see examples of both. Okay, and this is very much connected to the fact that the etale open topology on Kn may not be the product topology. Right, so if the etale open topology on K2 is the product topology, then the second item here will imply that it is a field topology. Okay, but it's often not. So I have this fifth item here is like a weak replacement for being a field topology, that it's invariant under affine transformations. So this and the fact that, like polynomials are continuous, that's often good enough. Okay, so now we have this topology, we have the notion of large fields, so I want to discuss the relationship between these two things. Okay, so here's the result. That your field is large if and only if the etale topology on the field itself is not discrete, and that's true if and only if the etale topology on the k-points of an arbitrary variety is not discrete, as long as that variety has infinitely many k-points. Now this condition of infinitely many k-points is necessary, right? Because the etale topology, it refines the Zariski topology, so it's always T1. So if there's only finitely many k-points, then of course it's discrete. Okay, but here I just want to say why 1 and 2 are equivalent. Okay, so we go back again to the same picture as before, right? We have this two-variable irreducible polynomial with a solution, and the second partial derivative is not zero at that solution, right? It's a non-singular point with a non-vertical tangent line. Okay, so now we let C be the plane curve that's defined by F. Okay, and now we think we have a morphism from this plane curve to the affine line that's just projecting onto the x-axis. Okay, now this projection is going to be etale at a point if that point is non-singular and if the tangent line at that point is not vertical, right? That's exactly what it means to be etale in this setting. Okay, and those two conditions, they define a Zariski open neighborhood of our point AB, right? So we have this subvariety and we have an etale morphism down to the affine line, right? This open subvariety is going to be cofinite. Okay, so first of all, if k is not large, then we can arrange, for there to be only finitely many points on this curve. Okay, now we can take the k points of the subvariety, take the projection. That's going to be a non-empty, finite etale image. Now, that's enough to get discreteness. Why? Well, first of all, the topology is T1. So if we have a non-empty finite open set, we can get an open singleton. And 2, the topology is invariant under translations, so if one singleton is open, then they all are. Okay, now, going the other way, if the etale topology is not discrete, then by the same argument, this etale image must be infinite, and that exactly tells us that this curve has infinitely many points. Okay, so yeah, that's what we see. Okay. Maybe it's also worth pointing out that if k is not large, then in fact the etale topology on the k points of an arbitrary variety is discrete. Okay, but I just want to emphasize now for a moment that what we're getting is okay, we get over an arbitrary field a topology so that this consequence of the implicit function theorem is satisfied, right? If we have, again, this kind of, same situation as before, then for any a prime that's sufficiently close to a in the etale topology, there's a b prime, so that a prime b prime is a root. Now, of course, if k is not large, then sufficiently close could mean equal to a, and it's trivial. Okay, but if k is large, then we get a topology where, this kind of consequence of the implicit function theorem holds. Okay. So next I'm going to talk about some examples. Okay, so first of all, if the field is algebraically closed, then the etale topology is the Zariski topology. Okay, and the same thing is true in the more general case when the field is separably closed. So in either of these two cases, right, what this really means is that every etale image is actually Zariski open. Okay, so in the algebraically closed case, that's just a consequence of the fact that if you have an etale morphism between varieties, like as a map between schemes, then the image is open, an open subset of the scheme. Okay, and then to go to take that up to the separably closed case, you just, again, need to use some standard fact about etale morphisms that I won't get into. Okay, so in this case, in particular, this is a case where, the topology on the product is not the product topology, and where the topology on K itself is not a field topology. There are other examples. Okay. So we'll see that there are also other cases where you cover some standard topology. Okay, now this other theorem, I won't say anything about the second one about how it's proved. I just put it in there to give some kind of a feeling for what this topology looks like in other cases, right? So in the case when K is not separably closed, the etale topology on K turns out to be Hausdorff. Okay, and we can generalize this to the K points of any projective or more generally quasi-projective variety. Okay, now we don't know if this goes up to arbitrary varieties. We tried, but we didn't get it. This really annoyed me for a while, but now I've gotten the impression that like no one cares about varieties that aren't quasi-projective. At least algebraic geometers don't. Because like I would try to, we formulated some kind of algebraic geometry question that would have implied this, and I like tried to answer people, and like they, I don't know, like they had no idea and they didn't really care. Okay, but I still would very much like to know if this goes up to arbitrary varieties or not, just to know one way or the other. Okay, so yeah, really now this business is really about non-separably closed large fields, right? That's the case where we get something that's interesting and possibly new. Of course, this Zariski topology is interesting, but it's old news. Okay, so now I'll talk about. Okay, so now on this slide, I'm going to again talk about some case where we recover like a known topology. Okay, so this is going to be the case where K is T-Henselian and is not separably closed. Okay, then the etale topology agrees with the T-Henselian topology on any variety. Okay, so it's worth pointing out here, I say the T-Henselian topology. Okay, and in fact, if you have a T-Henselian field that's not separably closed, there's a unique T-Henselian topology. Just like how, on a Henselian valued field, that's not separately closed, there's a unique topology. Okay, let me say this again, that any Henselian valuation on a non-separably closed field will induce the same topology. Okay, so again, if you don't know what this means, just think about it as covering these examples, right? So this shows that the etale topology over a real closed field is the ordered topology. It's like the etale topology on the field itself is the ordered topology. On the K points of a variety, it's the Euclidean topology induced by the ordered topology. Okay, and if you have like the p-adics or some kind of field of formal power series, you're going to get the valuation topology. Okay. So on this slide, I want to sketch the proof of this. Okay, and again, because, people necessarily know what T-Henselian means, to try to keep things also concrete, in red, I'll talk about what happens over a real closed field. Okay, I say here that I just want to talk about what happens over R, over the reals, but the same thing works over any real closed field. Okay, so I know this slide is kind of gross. It already took me approximately 10,000 hours in tech to make this. Yeah, I didn't want to put another 10,000 hours in. Okay, so first of all, over the reals, the implicit function theorem implies that any etale image is open in the Henselian topology. Okay, in the ordered topology, I guess. So that means that the ordered topology refines the etale topology. Same thing works over an T-Henselian field, but now, you're just using the implicit function theorem for polynomials, or polynomial maps, so we say algebraic implicit function theorem. Okay, so that's the direction is already given to us. Okay, so what we care about is to show that the etale topology refines the T-Henselian topology. Okay, and I'm just going to discuss that on K. Okay, to show that just on K, this is true. And once you have this on K, there's some general arguments that lift this to an arbitrary K variety. Okay, so first off, right, we're assuming that we're not separably closed, right? So what does that mean? That gives us a polynomial in one variable that's irreducible, that's separable, that has degree at least 2. Okay, so over the reals, the most natural choice of such a polynomial is x squared plus 1. Okay, now what does separable mean? Okay, what this means, okay, I guess together with irreducible, this tells you that the derivative of the polynomial is non-zero. All right, so this is one of these weird things that can happen in positive characteristic, is you can have well, okay, I guess whether it's weird or not depends on your opinion. This is at least one of these initially weird things that can happen in positive characteristic, is that you can have a non-constant polynomial with constant zero derivative. Okay, in characteristic 0, we don't have to worry about this. Okay, so what that means is that the set of points where the derivative is non-zero is cofinite. We call that u. Okay, now why does this matter? Well, a polynomial is going to be etale at a point. A one-variable polynomial will be etale at a point if and only if the derivative at that point is non-zero. Okay, so that means that the image of this set under F, this O, is going to be an etale image. Okay, so that means that it's going to be etale open, and by the first refinement, it's open in the T-Henselian topology. Okay, so over the reals, right, the only place where this polynomial has zero derivative is at the origin. So U is the set of non-zero real numbers, and O is the interval from 1 to infinity. Okay, now the polynomial is irreducible, right? So O cannot contain 0. Okay, but we see something stronger right over the reals, which is that O is bounded away from 0. Okay, that's going to happen in general. That's a consequence of T-Henselianity, right? That the 0 is not a limit point of O. Okay, now what this is going to imply is that if we take O and we invert it, it's bounded. Okay, so what do I mean? Okay, so over the reals or over a real closed field, you invert it, you get the 0-1 interval, which is bounded in the usual sense of linear orders. If you're working with like a valuation, you get bounded in the sense of the valuation, which means it's contained in some kind of valuation ball. Okay, and it's also going to be open. Okay, I say here that it's open in the etale open topology, but it's also going to be open in the T-Henselian topology. And the reason for this is because inversion on the multiplicative group is a homeomorphism in both topologies, right? So in the etale open topology, it's a homeomorphism, okay, because it's etale on the multiplicative group, which you can see just by computing the derivative. Okay, now, what boundedness tells you is that when you rescale this set, it becomes arbitrarily small in the T-Henselian topology. So that means that if you take translates of rescalings, you're going to get a basis for the Henselian topology, right? And okay, we know that the etale open topology is invariant under affine transformations. So all of the elements of this basis are going to be etale open. And that does it, right? We get a basis for the T-Henselian topology consisting of etale opens done. Okay, and over the reals, you get, the standard basis. Okay, so it's worth saying, like, where does this proof come from? So T-Henselianity was induced by Prestel and Ziegler, I believe in the 70s, and sometime after this, Prestel showed that if you have a non-separably closed T-Henselian field, then you can define in that field a basis for the topology, right? And of course, this is the definable basis that he constructed, is exactly this. So initially, we had some more complicated proof of this that involved like passing to a finite extension and pulling things down. And then we sort of looked at this and we were like, okay, if the topology is definable, then the proof of definability should give what we want as well. And it did. Okay, so now this shows that in many cases, we recover some topology that's already well known and interesting. Okay, so now I want to, for the rest of this talk, I'm going to talk about definable sets. Okay, because that's the original goal of this project was to find a topology over a pseudo-finite field so that definable sets were well behaved. Find like the equivalent of a pseudo-finite field for like the order topology over a real closed field. Okay, so the next results we'll be talking about are going in this direction. Okay, so now I'm really talking about, the model theoretic part. Okay, so suppose that the field has characteristic 0, and suppose that X is an existentially definable subset of m-dimensional space. Okay, so now what this says is that X is a finite union of etale open subsets of Zariski closed sets. And in fact, we can take these etale open sets to be definable. So in particular, as Anand pointed out during my talk, in particular, this means that X is a finite union of locally Zariski closed sets, where locally means in the etale open topology. Okay, so it's worth thinking about the case of a subset just of the field. Okay, now in this case, right, the only Zariski closed sets are either finite or the entire field. So this just means that X is the union of a definable etale open set and a finite set. Okay? Okay. So first of all, I state this for an arbitrary field, but of course, this is completely trivial if K is not large, right? Because if K is not large, the topology is discrete on every Km and every set is open. Okay, so I don't put large into the statement of the theorem just because the proof makes no use of largeness. The proof is purely general. Okay, now in the theorem, I suppose characteristic 0, this can fail in positive characteristic. Okay, so I'll give, I think, what I believe is the only example we know of when it fails. Okay, so suppose K is separably closed, not algebraically closed. Okay, now, the sort of model theoretic proof at this point is that, look, if you satisfy this condition with respect to the etale open topology, well, you're minimal, right? And so if all elementary extensions satisfy this, then you're strongly minimal and you have to be algebraically closed. Okay, but also, of course, we can see this much more directly. Just look at, the image of the Frobenius, the set of Pth powers. Okay, if you're separately closed and not algebraically closed, you aren't perfect. So this set is infinite. So it's dense in the Zariski topology, and it's co-infinite, so it's Zariski codense. Okay, but we believe that the real problem here is not really positive characteristic, but lack of perfection. Okay, so we believe that this result holds for perfect fields. I think we probably have a proof of this, but I'm not ready to talk about it publicly. It's harder. If it turns out that this is wrong, I'll like add some kind of comment to this video. Okay, so now, of course, the obvious application of this is to model complete fields, right? So if we have a field that's characteristic 0 and model complete, or that becomes model complete after you add some constants to the language, then every set is existentially definable, and we have the conclusion of the theorem for an arbitrary definable set. Oh yeah, so sorry, I should say also when I say, definable here, I mean definable in the language of rings, possibly using parameters, right? So when I say model complete, I mean model complete in the language of rings. Okay. So in either case, this just implies that every definable set is existentially definable. Okay, so this bit about adding constants to the language, that's actually significant because there are examples of fields that are not model complete in the language of fields, but become model complete after you add some constants. So if I remember correctly, pseudo-finite fields are not model complete in the language of fields, but if you add constant symbols for the algebraic closure of the empty set, then they are model complete. Okay, so in a number of cases, in many cases, we recover something that's already known, right? So for algebraically closed fields, right, well, in that case, the usual quantifier elimination tells you, in fact, the usual quantifier elimination is equivalent to saying that every definable set is a finite union of Zariski open subsets of Zariski closed sets. Okay, in the real closed case, it's a well-known consequence of the quantifier elimination for real closed ordered fields, and for p-adics, it's a consequence, I guess, of the quantifier elimination in the McIntyre language. Okay. At least I assume that's the case. I'm not too familiar with that setting. Okay, so I think it's pretty nice to get a proof that's uniform in the real closed and the p-adic cases. Or if you put these three together, it's like you have a uniform approach to all characteristic zero local fields. Okay, because I'm including, finite extensions of the p-adics. Okay, now what's most interesting is that this is covering new cases, right? So we cover pseudo-finite fields of characteristic zero. Okay, this characteristic zero assumption is annoying, but pseudo-finite fields are always perfect, just because finite fields are perfect, so we believe we'll cover that case with the more general results, which will also cover algebraic extensions of finite fields, which again are perfect. Okay, we cover a number of other examples. The only other one I mention is bounded pseudo-real closed fields. Okay, so bounded means that there are only finitely many extensions of each degree, and that here I mention that because that's the assumption that you need to get pseudo-real closed fields to be model theoretically well behaved, and in particular, model complete. Okay, so once again, this corollary is only trivial in the case when k is large, right? So this is really a result about large model complete fields. Okay, but ideally, you should be able to drop largeness. Okay, so McIntyre asked if every model complete field is bounded, and Königsmann conjectured that every bounded field is large. Okay, now, so in an ideal world, both of these implications are true, and model complete fields are all large. Now, certainly, both of these things are open, and it would be extremely nice to have either of these implications, but at least, these implications are true in all the examples, right? So at least all the examples we know of model complete fields are large. Okay, so for the remainder of this talk, I'm just going to talk about the proof of this theorem, which, as hopefully you'll see, is really not too bad. Like, somehow the topology is set up in a way that makes this kind of thing reasonable to prove. Okay. I feel like I'm forgetting to say something. But, oh yeah, what I was going to say is that, okay, this is also true for these kinds of fields of formal power series, this result, although these are not necessarily model complete in the language of fields. But in that case, it's a consequence of, like, okay, in characteristic zero, it follows from, like, the usual quantifier eliminations for, Henselian valued fields of characteristic zero. Okay. So now for the proof, I'm going to first have to introduce another thing from algebraic geometry, which is the notion of a smooth morphism. Okay, so this initially just really confused me because I thought that, like, somehow the name indicated to me that it should be like the analog of a smooth function in differential geometry, but that doesn't make sense because, like, any polynomial map, of course, is C infinity. Okay, so that's not what this is supposed to indicate. This is supposed to be really an analog of the notion of a submersion in differential geometry. Okay, so again, I'm not going to give the actual definition because it's one of these heavy algebraic things, but if you're talking about morphisms just between smooth varieties, it just means that you induce surjections between tangent spaces, right? Which is like being a submersion. Yeah, so I think the word smooth is because if you take the unique morphism from a K variety to a point, where the point is the spectrum of K, then that's smooth if and only if the variety is smooth. Okay, so first of all, we have this nice lemma that says that the map between K points that's induced by a smooth morphism is open. Okay, so etale morphisms are smooth in general, and so this tells us, this generalizes the fact that etale morphisms give you open maps. I won't say anything about the proof, except that, again, it's an easy consequence of standard facts about, relating etale and smooth morphisms. So in fact, we could go back from the beginning and do all of this in terms of smooth morphisms, right? And then really what this lemma says is that, like, the smooth open topology agrees with the etale open topology. Okay, so we're going to use this in a result that says that in characteristic zero, morphisms are generically smooth as long as some conditions are satisfied. Okay, so suppose the field is characteristic 0. Suppose that we have a dominating morphism between integral varieties. Okay, so what does integral mean? Okay, basically this means irreducible. It's like a strong form of connectedness. But the only thing that matters for us is that you can take any variety and you can decompose it into finitely many integral pieces. Okay, that's really all we need. What does dominating mean? What that means is that the image of V is dense in W. Okay, and that's equivalent to saying that the image of V in W contains a dense open set. So it's like almost like saying surjective, right? Now you need this, right? Because if you have like just say the inclusion from a line into the plane, okay, that's clearly not going to induce, or that clearly should not induce surjections between tangent spaces. Okay, so that's not going to be smooth anywhere. Okay, but under these conditions, the map is generically smooth. It's smooth on a dense open subvariety of V. Okay, right, so Sard's theorem, sort of gives you this conclusion in the setting of differential geometry away from a set of measures 0. But this is, right, we get a sort of stronger condition, a stronger conclusion in algebraic geometry. Okay, so first of all, this is not true in positive characteristic, right? Consider the Frobenius as a morphism from the affine line to itself. Affine line is integral, this morphism is dominating, and it's not smooth because constant derivative 0. Okay, so this is why it's even, the perfect case is a lot harder than the characteristic 0 case, because we don't get this kind of generic smoothness. Okay, so yeah, and this is a standard result in algebraic geometry. Okay, so now I'm going to show how we can use these two things to prove the result. Prove this result on, this tameness property for existentially definable sets. Okay, and we're supposing on this slide that the characteristic K is 0. Okay, so suppose we have a definable subset of m-dimensional space. Okay, what does this mean sort of geometrically? It means there's a quantifier free definable subset of a higher dimensional space so that the coordinate projection of that set equals x. Okay, so first we want to make a number of reductions, right? So first of all, we want to reduce to the case when, the quantifier free formula defining y is just a Boolean combination. Sorry, is just say, I don't want to say Boolean because then that would allow negations, but let's say that it only contains polynomial equalities. There's no inequalities. Okay, so now we just use this very standard idea in the model theory of fields of how you can remove inequalities. Okay, but I put this in here just because if you don't know it, it's worth knowing. Okay, so in a field, if you say that x is not equal to y, that means that x minus y is not 0, which means that x minus y is invertible, and you can express that with this existential formula that contains inequality. Okay, so we can remove inequalities from formulas at the cost of adding more existential quantifiers, which is fine, right? Geometrically, that's just raising the value of n, which doesn't make a difference. Okay, so what does it mean that we've reduced to this case where we only have equalities? What that means is that y is the k-points of some closed subvariety of affine space, right? Where this v is going to be the variety that's, defined by these polynomial equations. Okay, now we can make a further reduction to supposing that v is integral, because if it's not, we can decompose it into finitely many integral pieces and prove the result for the projection of the k-points of each piece separately. Okay, so as one often does, we're going to apply induction on the dimension of v. The zero-dimensional case is trivial. The dimension is 0, v is finite, so x is finite, so x is just Zariski closed. Okay, so now let's think about the general case. And here we're going to use some combination of the lemma and algebraic Sard theorem. Okay, so we think about this projection from the variety down to m-dimensional affine space as a morphism. Okay, the obvious obstruction to applying the algebraic Sard theorem is that this may not be dominating. So we fix that by just restricting to the projection to the Zariski closure of the image, right? So now we just immediately have a dominating morphism. Okay, the algebraic version of Sard's theorem that tells us now that this projection is generically smooth, so we find this dense open subvariety on which it's smooth. The lemma tells us that if we take the k points of that dense open subvariety, look at their projection, that's in a tall open subset of this wk, which is a Zariski closed set. So we found one etale open subset of a Zariski closed set that's contained inside of X, right? Okay, but that's not going to be all of X because, we aren't picking out all of V, but because U is dense and open, what remains in V has lower dimension, right? So by induction, we get the same result for the projection of the k points of the rest of V, and that gives us the result for all of V. Okay, and that does it. Yeah, so this is almost like, especially in characteristic zero, somehow this can almost feel a bit too easy, but I think, okay, like that's what you need for the result, but to actually know if the result, is interesting at all, you need to know some things about the topology, right? So you need to know non-discreteness, and you need to know that in many cases you recover some known topology, right? So really we need all of the, right? We only need this slide to prove the result, but to care about the result, we need everything else from the talk. Okay, so finally, let me just discuss some future things we need to do. Okay, we need to handle the perfect case. We need to finish that off. Okay, but now, of course, there are model theoretically tame fields that are not model complete in the language of fields. So we want to handle them too. So one example is perfect Poc fields. Okay, there is some description of definable sets in them that I think should give us the same result, but with a more difficult proof. Okay, now secondly, if you care about definable sets in separately closed fields, you don't want to be working with this risky topology. So, ideally there should be some other topology that's defined in a sort of similar way, where a similar result is true for separately closed fields. Okay, now finally, okay, so originally we proved this result, right, for existentially definable sets. And of course we did that just because we wanted to understand the model complete case. But it is interesting to get this result for existentially definable sets, in an arbitrarily large field. Right, so this shows somehow that existentially definable sets in any large field are tame in some sense. And that's interesting because definable sets in an arbitrary large, okay, and at least perfect or characteristic zero field are not necessarily well behaved. So if you take a ring of formal power series in more than one variable, if you take the fraction field that's large, okay, I think that's also due to pop. Okay, but it's known, I forget who this is due to, that this does define the subfield of rational numbers, and hence, defines the integers by a theorem of Julia Robinson. So this kind of structure is completely wild. But somehow what this result indicates is that, maybe the existential theory of this structure is still tame, and we can, salvage some kind of tameness, which would be nice. It's always been sort of, it's a bit unsatisfying that this is wild in some sense, because if you take formal power series in one variable, then it's, it's NIP and DP minimal. Okay, so, and there already is some indication of this, right? It's there's this theorem of Fem, that if we have a perfect large field, it doesn't existentially define any proper subfield. And so in particular, it cannot existentially define the rational numbers. Okay, so let me also just point out finally that we can use our result actually to give a topological proof of Fem's theorem in characteristic zero. Basically, you can show that if, okay, it's pretty easy to show that if we have any proper subfield that's open, then the topology actually has to be discrete. Okay, that's something that's also true in topological fields, and a proof of the right level of generality goes through in this setting as well. Okay, but in fact, in the perfect case, our approach to a proof is using ideas from Fem's paper. Okay, so that's all.